Welcome back to the course Rocket Propulsion offered by Edal Systems. In today's class, we will discuss about an example demonstration. So how we can solve a 2D nozzle problem which is used in rocket propulsion, that is how the flow behaves and how we should set up a problem of a nozzle in ANSYS Fluent. So this will be the 2D geometry we will be using for the problem, that is we will have a nozzle inlet. So from here the hot exhaust gases will be expanding throughout the length. So the flow is moving from the left side to right side, that is the direction of the flow. Then we have an outlet. Then the line which we are using bottom, that is we are just considering half geometry to reduce the computational time. So we are using a symmetry geometry. Then we have nozzle walls, that is this entire region is consists of nozzle wall. Then this region and the upper region, that is considered as far field. So using far field for an external flow problem is very important when we are doing an analysis. So we will be modeling this geometry, that is we will be using this geometry for our simulation, that is flow will be entering from this nozzle inlet and then it will be allowed to pass through the entire geometry. Just to understand or to get an idea how we can simulate or what are the values for such kind of rocket propulsion problem, we will be using this geometry. That is, we can simulate it in many different ways, like mixing is one problem, then combustion of these propellants is second kind of problem, and expanding them through a nozzle is another kind of aerodynamic problem. So the third option we will be simulating in our course today. So we will see some of its details. So this is the mesh which is done for the following geometry, that is only 9030 elements are used, so that it will be easy for everyone to use it in their ANSYS Fluent, because some laptops will have very general kind of specifications. So it has average skewness and minimum and maximum values as given. So to define this kind of problem in ANSYS Fluent, these are the boundary conditions which we'll be using. So basically it will be a very turbulent flow, so we'll be using K epsilon model, that is K epsilon realizable model we'll be using to model the turbulence terms. And we know that temperature is also involved, because such high temperature gases will be expanding from nozzle. So we'll be using energy equations as well. So boundary conditions, we see that for nozzle inlet we'll be using a pressure inlet boundary condition, because here we have the data of the pressure values at which the propellants enter the nozzle region. Because we have temperature and pressure values, we can also calculate velocity values, but instead we can use these pressure values directly as pressure inlet boundary condition and specify these properties over there. So at this high pressures, the propellants will be, or the exhaust blooms which are created inside the combustion chamber, will be entering through the nozzle inlet and they will be allowed to expand throughout the body. And at outlet we are using the pressure outlet condition, again where we are specifying the gauge pressure. Then symmetry line will be using it as an axis, so that we'll be able to visualize the whole nozzle flow when we do the post processing. Then nozzle wall and far field, these all things will be considered as wall itself. So let's go and start the problem in ANSYS Fluent. So here I have opened the geometry and the mesh file. So we will go directly into the setup and we will set all the things which we need for our simulation. So we will be using ANSYS Fluent here. So mesh is already taken, so it is 2D mesh and we have to go with double precision and display mesh after reading. So I will just reduce the number of processors to use. I will just go with the 2 processors and start. So here we can see that our geometry is ready, that is the mesh has been imported and the structured mesh is visible from this display. So we can view it and we can check for the mesh over here also. And one very basic thing which we need to do when we have done with importing the mesh is to check the mesh, that is we need to check the quality and the volume which is given. Then we have to go for report quality. So there are no error messages and we can proceed with the mesh. So as discussed that this is the nozzle inlet, this is the symmetry line, this is the outlet, these are the nozzle walls inside, and this line and this surface denotes the far field regions. So we will be using density based solver, that is density based. Why? Is because we are dealing with compressible flows now. So for modeling compressible flows we have to enable density based solver. Then we are using an axisymmetric geometry, so we have to select this axisymmetric over here. So it will give you some warnings over here. So we will look into these warnings one by one. So now solver has set to density based solver, and time scheme will be dealing with steady, and 2D space will be axisymmetric. We will directly go into models, and we have to switch on the energy equation model because we will consider the temperature differences as well. Then turbulence model, that is viscous model, we need to go with K epsilon model and realizable, and we have to click OK. So viscous model and energy model are done. Then we will go into materials, that is air will be used as a fluid here, and we will change some of the properties, that is density will be using ideal gas over here, such that the density will keep on changing according to the ideal gas law, and also we'll be changing viscosity to Sutherland law. Sutherland law provides very efficient and accurate results for the change in viscosity. There are other options as well to solve this all properties, that is density we can go with constant, incompressible ideal gas, and many other options are there. But for now we'll be using ideal gas option. So just we need to click on change create such that these values are enabled for density and viscosity. So just close this window. We will go into cell zone conditions, that is what these cells should denote. So the solid surface body, that is this entire body, will be considered as fluid region, that is we call it as cell zone conditions. We'll just take a look over here. So we don't have to do anything over here, that is just what fluid material we are using. So we just have one option, that is air. When we are dealing with multiple streams, then we can change this option. Now let's go into boundary conditions and we will see different boundary conditions. So as discussed, we will be using pressure inlet boundary condition. So we will change this to pressure inlet. So this is the dialog box for pressure inlet. So we have to specify the gauge total pressure over here and supersonic initial gauge pressure. So gauge total pressure which we have to specify, the values I have mentioned here in PPT, that is 2268000. So we will put these values in gauge total pressure 2268000, and the supersonic initial gauge pressure will be 2267000, just 1000 less, 2267000. So the pressure has been specified. Now we have to go and we have to change the temperature. So this 300 we will change it to 1200 kelvins, and we just have to give OK. They all come under internal, and outlet we have to specify is pressure outlet, and we just have to give one property for the pressure outlet here, that is we need to change this gauge pressure. So what gauge pressure we are using at outlet is 39368 pascals. So we will specify it 39368 pascals. Then thermal, that is 300 Kelvin we are using. So that's it, it is done. We don't have to change any other thing. So now in console, if we see that warning is given that it appears that symmetry zone 7 should actually be an axis. So we need to change the symmetry to type of axis. So we are done with that. Outlet is there, and far field and nozzle walls are walls. We don't have to change anything here. So models are specified, then cell zone conditions are done, boundary conditions are done. So let's go to reference values and put the reference values from inlet. So all the references for this simulation will be taken from the inlet geometry. Then let's go to methods, and we need to change this to second order to get more accurate results without any stiffening. Then we can go into, let's say, monitors, and we will see change of temperature at the outlet resulting with change in each iteration. So we will go into report plots, new, and select this new option, and as we will be doing it on surface, so we'll select surface and mass weighted average value. So here we can specify what property or what field variable we need to see. So temperature, static temperature, and we want to see it at outlet. So I can change the name here. So temperature at outlet. So report plot, report file, and print to console. So we will be able to see the change in temperature at outlet with change in each iteration. So just give OK. This done. And let's check for one convergence criteria over here what we have. We go into residuals. So here we have convergence criteria of 0.001. So we will see how this happens. Give OK. Now we have to initialize our solution. So we will be using hybrid initialization technique. So let's get to initialize. And it is done. So we'll come into run calculations. And first thing we will do is we will do check case. So it will show if any recommendations are there. It is showing that non-zero operating pressure set. This will be added to gauge pressure inputs. So boundary condition, click operating condition. So we need to change this condition, that is the operating pressure which is specified. So we need to change this operating pressure because it will be more higher value. So operating pressure is the pressure inside this system. So we will go into boundary conditions and operating conditions. So here operating pressure is given in Pascal, so we need to make it 0. Then that is done. Okay. We will again go to run calculations and check the case. So now there are no recommendations to make at this time. So we will just go and we will give some 500 iterations. And we will check the results once it is done. So I will click the calculate button. And we will see how these residuals are varying at each location. Also, we will see how the temperature is varying at the outlet surface for each iteration. So here the calculation has started. So once it covers 500 iterations, we will see some basic results. So the calculation is done. So we will check the residual plot and the temperature change. So from 1200 it has gone down to around 600 kelvins at outlet. So what we will do is we will go to workbench back. So we can see setup is done, solution is done. So we will click on results. So these results will be opened into a different window that is called a CFD post. CFD post is a tool used for post processing. So we can visualize our results more clearly in this CFD post. And every time when we are opening anything, then we can see the status over here, that is it is showing opening CFD post. So here we have our geometry. So we'll just click this Z to view it in this direction. Now what we have to do is we have to create a contour. So we'll click on this icon here and we will give this name, click OK. And here that is which domain we want to see, we can select. So it will be all domains, and locations we have to select. So as we move from one location to another location, we can see a change is happening. A pink line is highlighted into the surfaces which we are selecting. So this one is far field, this one is inlet, and this is nozzle wall, this is outlet, this is the symmetry line, this is the hole mesh. So we can select this periodic one, that is mesh, and we can select the variable which we want to see. So first we will look out for velocity and we will give apply. So this will give us the velocity contour. Now we have to change this number of contours to 11 to say 100, and I will just place it a little bit this side so it is clear to see. So 100 is, we will change this 100 to say 150 and give apply. Okay, so for 150 we have got a temperature, velocity contour. Now we want to see the change what is happening at the second mirror image also. So what we will do is we will create another contour, contour 2, and we will go into view and we have to click this apply reflection or mirroring, and then we have to select the plane. So for our plane, ZX is the perpendicular plane which we'll be using, because here we can see XY is there, so perpendicular plane will be ZX. We have to go and change this to periodic 1 and this to velocity and number of contours to 150 and give apply. Okay, so here we have a velocity contour for the complete geometry, that is complete nozzle, and the maximum value which it has reached is 1381 meter per second. It's a very huge value it has reached. So what we will do, we will go back into our residuals. And in any CFD analysis, it is necessary to solve the conservative equations till we get the same amount of results. That is, we are solving it again and again to that particular equation And even if the solution is not changing, then only we can say that a solution is converged. So basically that is defined when the residuals reach 1 e to the power minus 3 difference of the residuals. So we have to solve these iterations till we get a converged solution, that is till these all 6 variables reach at least 1 e to the power minus 3. So what I will do, I will just change this 500 to, let's say, 1000, and then I will click calculate. You have to select OK here. We'll give calculate, and then we will solve it for next 1000 iterations, and we will see if these residuals are reaching to 1 e to the power minus 3 value. And here we can see the change is happening because still it has to solve, and we can see the temperature is still changing. So we need more converged solution over here. So once it finishes 1000 iterations, we will go back into CFD post and analyze these results. And we will be able to see a change happening in that particular region for this more 1000 solved iterations. So again here the next 1000 iterations are completed. So we will directly go into CFD post, and here it will ask you that new upstream data exists. Do you want to refresh the simulation? You have to always click on yes, such that this result will be displayed with the updated number of iterations, and we can instantly see the change happened. So this is how the change has happened with more 1000 iterations, that is total 1500 iterations are solved, and the far field is getting more and more clear, and we can see that the flame is reached to a more wide region, and the maximum value of velocity which it has reached is 1422 meters per second. So this plot we have here for velocity. Now if we go back into Fluent, then we can see that temperature is almost remaining constant. And if we check for the residuals, then K epsilon, they are coming down to 1 e to the power minus 3 residual, but still the continuity x and y momentum and energy has not reached to 1 e to the power minus 3 value. So what we have to do, we have to solve more 1000 iterations and get more accurate and clear results. So I will just go and click for calculate. So next 1000 iterations are solved and calculation is completed. So we can still see that the three variables, that is continuity, x velocity and y velocity, has not reached to 1 e to the power minus 3 difference. That is, it has reached to e to the power minus 2, and soon it will be reaching to 1 e to the power minus 3. That is, we need some more iteration to solve. Just go to the temperature, we will check. So this is the temperature variation. So we will go into CFD post and check for the results as well, if there is any major change happening. So as we are solving more and more iterations, we can see that there is change happening in the flow development. So now this lighter blue region, that is the region of higher velocity, is increasing compared to other velocity regions. So we need to see more accurate results. So what we will do, that is, we will go for more 1000 iterations, and lastly we will check. The calculation is complete for more 1000 iterations, that is total 3500 iterations are solved till now, and we can see the temperature difference here. So we will go back to the results and we will click yes over here. So we can see that this region is getting more and more developed as we are moving for more number of iterations. So now what we will do is we will check for the temperature contour. So this is contour 2. In contour 2, what we will do, we will change this from velocity to say temperature and give apply. So this is the different one. We will have to go to contour 1 and do the same for the contour here, and give it temperature, give apply. So this is the temperature difference happening here, that is the maximum temperature reached is 1600 kelvins over here, and we saw for the pressure as well. So we can go and we can calculate the exact numbers using this function calculator. So here we have to click on calculators and then select function calculator, and function we need is average value. So we will select this AVE, and location, let's say at inlet, and then we will select the variable. So we will select variable as temperature. We will see what is the average value of temperature at the inlet. Get calculate. So 1123 is the average temperature value at the inlet, Same we can check for outlet. So if we go and change it to say outlet and click calculate, so it has reduced to 436 kelvins. So one more thing we will check is velocity. Go to velocity and click apply. So this velocity is at outlet, it is 1200. With such high intensity or such high velocity, it is moving outside. We will check for inlet as well. Calculate. So at 391 meter per second, the flow is entering from this region. Then it is get expanded to 1200 meter per second. So we want to see the Mach number variation as well. So we will go back into the Fluent, and what we will do is we have to click on file. We have to go to say data file quantities. So here the dialog box which we see, these are the standard quantities which are included into CFD post. So you just have to click on this additional quantities which you want to add into CFD post, select it and then click OK. So this will be added. So now what we have to do, we have to solve 1 or 5 equations such that a new data set is created and we can see it in CFD post. So give calculate, click OK. So just 5 iterations to solve to get the results inside CFD post. OK. And if we go into CFD post and click yes, so we will directly go and check for the Mach number variation. This velocity we will change to Mach number. Hope it has to come. Yeah, it is there. So we will check this average Mach number at inlet 0.5. Same we will check for outlet. Click outlet. So 3.1 is the Mach number, average Mach number at outlet region. We will do is we will check for the contour as well for the Mach number. So contour 1, we need to change this variable to Mach number and give apply. So this will be Mach change. Same we need to see for the contour 2. Change this temperature to Mach number and click apply. So this is the Mach number variation. So we can see at outlet it is expanding with very high velocity. Around 3.1 average Mach number it is showing at outlet. But if we check for a maximum value, then it is showing a 5 Mach number. That is, it is reaching to 5 Machs in this simulation. So this is how exactly we see any rocket launch. Then we are able to see the variation happening. The smokes which come out of the booster rockets, this kind of flame we see. So the blue region which we are able to see here is the flame which is generated, which is the actual shape for the exhaust gases which are coming out of the combustion chamber. So with this we finish the simulation, and the summary for today's class is that first we have seen the steps to simulate a rocket engine simulation through a 2D nozzle in ANSYS Fluent, and different post-processing techniques used in CFD post we have discussed for a rocket problem. So with this the course rocket propulsion is finished. Thank you.